Isn't it kind of wild how a simple piece of curved glass can totally change how we see the world? I mean, it can make things look huge, shrink them down to nothing, or even flip everything completely upside down. Well, that's the magic of lenses, and today we're going to pull back the curtain and see exactly how they pull it off.
So here's our game plan. First, we'll get to know the two main types of lenses. Then, we're going to learn how to predict the images they make. First, by just drawing it out, and then with a really powerful formula. And finally, we'll figure out how to calculate an image's size and whether it's right side up or not.
All right, let's start at the beginning. What are we even talking about when we say the word lens?
At the end of the day, a lens is basically a light bender. It's just a piece of clear material, usually glass or plastic, that has at least one curved surface. Its whole job is to take the light that passes through it and bend it, or refract it, in a very specific, predictable way to create an image.
Okay, let's meet the two heroes of our story. First up, we have the convex lens. You'll notice it's fatter in the middle. This one's job is to pull light rays together to make them converge. Then we have its opposite, the concave lens. It's thinner in the middle, and it does the exact reverse. It spreads light rays out, making them diverge. It's like with glasses, right? A convex lens helps far-sighted people by focusing light, while a concave lens helps nearsighted people by spreading it out first.
So we know lenses bend light, but how do we figure out where an image is going to show up or what it'll look like? Well, the easiest way is to just draw it. So let's check out this graphical cheat sheet for light, ray diagrams.
Now, an object is shooting off light rays in every possible direction, right? An infinite number of them. But here's the secret. We don't have to trace all of them. We only need to follow 2 or 3 special rays, because their paths are super easy to predict. And get this, wherever these special rays cross paths on the other side of the lens, that's exactly where our image is going to be.
Okay, so let's learn the rules for these special rays. Rule number 1, and this is a big one, any ray of light that comes in traveling parallel to that center line, we call it the principal axis, will get bent by the lens so that it passes right through one special spot, and that spot is called the principal focus.
Now, Rule 2 is just the perfect reverse of Rule 1. It's beautiful, really. If a ray of light passes through the principal focus first, before it even hits the lens, it will come out the other side traveling perfectly parallel to the principal axis. See that symmetry? It's pretty cool.
And now for the easiest rule of them all. Seriously, this one's a freebie. Rule 3. Any ray that goes straight through the dead center of the lens, the optical center, doesn't bend at all. It just keeps on going, in a perfectly straight line, no questions asked.
So let's put it all together for a convex lens. We just draw our 3 special rays coming from the top of our object. And look at that. They all cross over or converge at one single point on the other side. That tells us exactly where the top of our image will be. And you'll notice it's below the center line, which means our image is upside down or inverted.
Drawing these diagrams is awesome for getting a quick idea of what's happening. But, our drawings aren't perfect. For real science, for engineering, for times when we need to be absolutely precise, we got to bring in the math.
Now, before we can jump into any formulas, we need to agree on a set of rules, a kind of universal language for how we measure things. Think of it like a GPS for our calculations. It's called the New Cartesian Sign Convention, and it just makes sure we're all on the same page.
The rules are actually pretty simple. Everything gets measured from the center of the lens. Then we just assign positive or negative signs based on the direction of light, or whether something's above or below the center line. But here's the single most important thing to remember. Convex lenses have a positive focal length, and concave lenses have a negative one. That little detail is the key that makes all the math work out.
Okay, time for the main event. Now that we've got our rules of the road, we can finally unlock the power of the lens formula. This is what connects everything we've talked about.
And here it is. This elegant little equation is the lens formula. It perfectly connects the object's distance from the lens, which we call u, the image's distance, v, and the lens's focal length, f. If you know any 2 of these, you can always find the third. This is the engine that tells us exactly where an image is going to form. No guesswork needed. Let's just walk through a quick example. Let's say we put an object 15 centimeters away from a convex lens that has a 10 centimeter focal length. Using our sign rules, u is -15 and f is +10. We just plug those numbers into the formula, do a little bit of algebra to solve for v, and bam! The answer is +30 centimeters. That plus sign tells us the image shows up on the other side of the lens. Simple as that.
So we know where the image is, but what about its size? Is it bigger or smaller? And is it right side up or upside down?
This is the final piece of the puzzle, magnification. So the formula for magnification, which we call M, is just the image height divided by the object height. But even better, it's also equal to the image distance V divided by the object distance U. So we can use the numbers we just found to calculate the magnification super easily.
But honestly, the most powerful thing about this calculation isn't even the number itself, it's the sign. If your answer for magnification is positive, it means the image is upright or erect. If the answer is negative, it means the image is inverted or upside down. That tiny little plus or minus sign tells you so much about what the image looks like.
When you get a negative magnification, that means you have what's called a real image. This is a really important idea. A real image is formed where light rays physically cross paths. It's the kind of image you can actually project onto a screen, just like a movie projector does. And a real image is always inverted.
On the other hand, a positive magnification means you've got a virtual image. In this case, the light rays don't actually meet up. Our brain is just fooled into tracing them back to a point where they look like they're coming from. This is the kind of image you see when you look into a mirror or through a magnifying glass. You can't project it onto a wall, and it's always upright.
So, to wrap it all up, here's a super handy summary. A convex lens will almost always give you a real, inverted image, unless you put the object really, really close to it. A concave lens, though, is way more predictable. It will always give you a virtual, upright, and smaller image, every single time.
So, we've just cracked the code for how a single lens works. But the real magic, the stuff in your phone's camera or in a giant telescope, happens when you start combining them. How do all those lenses work together, using these same basic rules? To bring a distant galaxy or a tiny cell into perfect focus? Well, that's the next adventure in learning how to bend light to our will.